Okay, recording in progress. Share. Everybody can see that, correct? Yeah. So, and sharing here, I want to just use the pen of this WebEx. Unfortunately, I don't have the laptop of the university is not a touch screen, so I have to use my mouse. The laptop of the university I'm using with all the software in it, so it does not have a touch screen. So therefore, my writing will be a little bit awkward because of the mouse is acting like a pen, and that's very difficult. But anyway, so we went to our first example. We said we related the moles is equal Avogadro's number of particles. Those particles can be molecules, atoms, or formula units or ions, correct? And we define the mole as a ratio actually between amount of mass divided by the molar mass, correct? Now, we have two types of Avogadro's calculation. They call it Avogadro's calculation, stoichiometric Avogadro's calculation. You will be given the mass. Let me just see it. So you'll be given the mass and you will be asked to get the number of particles, whether the number of atoms or molecules or ions, formula units. And this goes this way here. So there are two steps here. So we are from going from the mass to the number of particles. So the mass always small amount. So this small amount, so amount small, so small amount. I mean, I can't write with this amount. I'm writing with the mouse is not good, but I'll make an error. Amount is small here. Amount is very, very high. So how to relate the mass of a particle and get out of this number of detailed particles, molecules, atoms, or ions? Well, first step here, you have to divide. The first step is, if you have the mass, you have the first step here, two steps we say. From mass, small amount, to larger amount, particles amount, you have to divide by molar mass or atomic mass. Divide by molar mass if you have a molecule, or atomic mass if you have an element. Molar mass, molar mass. That's the first step. The next step is you have to multiply by Avogadro's number. Multiply by Avogadro's. So I've abbreviated here, Avogadro's number. Okay, guys. Now, if I want to go the opposite way, so what should I do? Well, it turns out to be, you have to reverse this one here. You get number of particles, you have to divide by Avogadro's number, and you multiply by the molar mass to get number of grams. So let's look at here an example here. We are looking at this example. 10 grams, this is 4-6 of carbon. How much is 10 grams of carbon? How many atoms in this 10 grams of carbon? So that's it, or how many molecules? So it turns out to be, take this is a carbon, an element, not a molecule. You divide this one here by its atomic mass. This is the atomic mass of carbon. Cancel the gram with the grams, you get moles. Then you multiply by Avogadro's number, the moles here cancels with the moles, and you get this number here. Remember, this is 4 sig figs. This is 5 sig figs. This is 4. Your answer has to be 4 sig figs. Okay, your answer has to be 4 sig figs. So now let's look at the second option here. This one here. So I'm going for the second one. I'm going from the larger number of molecules or atoms or ions, and it is from large number to small number, which is grams, correct? From small to large, I mean from large to small. So the first thing here is you get rid of this large number here, large number, by dividing by Avogadro's number. Then you have the moles to the mole here, you get rid of the mole here, whatever you get number of moles, you use the multiplying by the atomic mass of carbon. So that's the two cases of the stoichiometric Avogadro's calculation. You go from mass to molecules or atoms or ions, or vice versa, from atoms, molecules, and ions to number of grams of the mass. So let's look at the at some examples here. We might have to look at some of the examples here. This is just in this diagram. If you look at this diagram here, this diagrams give you the whatever we said. When you go from grams, small amount, correct, to larger amount here. So you can expect here the amount will be large. Your answer will be large from mass in grams into number of atoms or molecules or ions. You expect the value will be large. So the first thing is to divide by the molar mass. It is here. Divide by the molar mass. You multiply by, here you divide, and then you multiply by Avogadro's number. Now, if you go the opposite from ions or atoms, you divide by the Avogadro's number, correct? See here, and then you multiply the opposite way. You multiply by the molar mass of that element or the compound. Okay, guys. Here, just give you an example. This example here is giving you to convert moles in atoms. So you are skipping the gram, the mass here. So are you following me here? So you are skipping here the mass. There is no mass here. It's given to you the moles, correct? Just if you need the moles, and you know that's 1 mole equal Avogadro's number, you just multiply whatever moles here you have with the Avogadro's number to get number of atoms or molecules or ions of that element, correct? So this is the topic here. You can look. Here is the same thing here. Ask you about, give you a compound, correct? This compound here, as you can see, 0.2 grams of the compound of H2O. This time we have a compound, not an element. So you follow the same thing. The only thing here, because this is a molecule here or compound molecule, small amount, you have to get the molar mass of this. Hydrogen is 2 grams per mole, correct? Because 2 of them here, 2. The atomic mass of hydrogen is, we just put it 1.0, and then you have 2 of hydrogens here. So this is 2. And then oxygen is 16. Oxygen is 16.0. So the only thing here, the molar mass of H2O is 16 plus 2 is 18. That's the only thing new in the calculation. So you do the same thing. You have the grams here, small amount, and you need the larger amount, which is the molecules. So the first thing is you divide by the molar mass, and then you multiply by Avogadro's number. And that's what we did. We divide here, look at this, by the molar mass, and then here it is, multiplied by Avogadro's number. I think everything is okay. Everything is okay. Any question you have, you can unmute yourself. If you have any question, please. Okay. I assume everything is good. Okay, so let's clear this and go for the next one. Now you can do those calculations easy. Just the only thing is we are dealing with the molar mass of a molecular compound or atomic mass if you have an element there. From small amount grams to large amount molecules, atoms, ions, 2 steps. You divide, as I said, you divide by atomic mass or molar mass, you multiply it by Avogadro's number to get the larger number. To coming from large number molecules, atom, ions to get number of grams, well, you have to divide first by Avogadro's number and then multiply by atomic mass or molar mass. So that's I think will be enough. We will go now to topic we'll go topic it's called the empirical formula. Well, what is the empirical formula? It turns out to be the empirical formula here versus the molecular formula. You can look at those examples. As I said, you have the right to print those examples and put them in front of you for the quizzes and exams. It's open book, so you can print them out and keep them handy so you can look into this. You can do all this is open book and except the phone. Cell phones are not allowed. So, cell phones are not allowed. So let's look at the empirical formula. What we mean by empirical formula? It turns out to be empirical formula here is different from molecular formula. So we have 2 types of formulas. Okay, those formulas are called molecular formula, and then the other one called empirical formula. So, well, if I look at the cyclohexane, for example, cyclohexane, so cyclohexane 6H12 is a cyclic. It's a cyclic compound, not aromatic. It's cyclic. And all in all, those here hydrogens is sticking out. Hydrogens is sticking out here. I said the mouse is not really so anyway. So all those hydrogen, you have 12 hydrogens, 12 here, and 6 carbons. Now this is a true ratio, so 6 to 12. This we call it molecular formula. The molecular formula is a formula that's really expressing the true ratio of the element within the molecular compound, the true ratio of the elements within the molecule of the compound. So we have 6 carbons to 12 hydrogens. Now the empirical formula, that's a reduced ratio. It's not a full ratio, it's a reduced ratio of the element within the chemical compound or molecules. So this is molecular formula, okay? I want to make out of this empirical formula, what's the common factor? 6. So I say C1H2. C1H2, this is the empirical formula. This is what? This is the empirical formula. It's a reduced ratio. It's not full true ratio like the molecular formula. And sometimes this empirical formula is really used to determine the molar mass. So whenever you do some elemental analysis, compound, you don't know its molar mass, and you don't know the ratio of the whole elements within this compound. So you can do an experiment, determine the empirical formula, and then from the empirical formula, you can get out into getting the actual true ratio between the elements within the molecular or compound, correct? So, and we'll start looking at some of the, how we can determine the this empirical formula. So it turns out to be several examples, and the well-known one, and it comes, I think, in the final exam, ACS exam, will give you the percentage of each element within a compound. Percentage. So we have whatever the cyclohexane, give you the percentage of carbon, the percentage of hydrogen. Percentage. So whenever you're approaching this, you assume whenever given to you the percentage of empirical formula, you assume that the whole molecule is worth 100 gram. 100% means 100 gram. And then from this 100 gram, you go for using the atomic masses of carbon and atomic masses of hydrogen. You can determine, correct? You can determine the number of moles. If you get number of moles, you divide then the ratio between those two elements with the least number of moles to get the least or reduced ratio. Let's look at the example here. Maybe if I'm talking not help, it will help to look at real examples. So let's look at real example here. And this time will give you, this is the flow chart or the diagram, how this one here, how this empirical formula is determined and assigned. And that's what I talked in a couple of minutes ago about this. So I give you percentage and then you transfer this percentage at the end to moles, correct? This is this percentage here with assumption that the sample is 100%. You go correct with the help of the atomic mass of each element, you can get number of moles. You divide by the least number of the moles to get then the empirical formula. So let's look at the example. Maybe the example will help us understand much better. Yeah. So let's look at the example here. And this type here, we're not asking about the empirical formula per se like this. This one will give you the percentage of each composition of each element. Wants from you how many percentage nitrogen inside this compound, how many hydrogen in this compound. That's ammonia, nitrogen trihydride. So we want to know what is the percentage. That's not per se, you can work it out from here and you can get the empirical from the percentage. So this is just the percentage of each element within the molecule, but you can work it out to get the empirical formula, which is here. The empirical formula will be 1 to 3. And this is really 1 to 3. Sometimes the empirical formula will equal what? The molecular formula. I mean, you cannot reduce this further than this. So 1 nitrogen to 3, you cannot reduce it further. That is empirical formula of ammonia as well as the molecular formula, because it's a true and reduced. So that's what you have. Both of them are the same formula. So how we get the formula of each element here, nitrogen, hydrogen? Well, you have to look first the molar mass of ammonia. You need the molar mass of what? Of the whole molecule. And the molar mass of the whole molecule is here. You have 1 nitrogen and 3 hydrogens equal to 14. Nitrogen is 14, 1. Correct, that's the one here. And 3 hydrogens. So 17 gram per mole is the molar mass of ammonia. Then nitrogen percentage will be, you divide the whole thing, that's the whole, and you divide each element atomic mass here by the molar mass of the whole molecule. Each atomic mass of each element by the molar mass, and you have to consider how much is this present. Nitrogen is 1, correct? And this one here is 3. So you have three atoms of hydrogen and 1 atom of nitrogen. And that's what you do for nitrogen. 1 multiplied by 14 divided by the whole molar mass, 17 grams. You get 82, and 17.6 is hydrogen. Now let's look at another example of this. As I said, this is just examples. This chapter, I think I wrote this chapter myself. And the only thing I just wanted is just put a lot of examples, because that's what you did. This another example here. You have thiosulfate, sodium thiosulfate. We need to see, calculate the rate, the percentage of each element. Sodium sulfate is Na2S2O3. How much sodium percentage is present, how much sulfur percentage is present, and how much oxygen, correct? And we can do it this way here. Again, you need the molar mass of the whole molecule, and then you divide each atomic mass of each element by the whole molar mass. And you have to consider the ratio is 2 sodium. You multiply 2 sodium by its atomic mass, divided by the molar mass of the whole molecule. So see here, sodium, atomic mass of sodium, and we have 2 atoms of sodium here, multiplied by the whole molar mass. And here is how to calculate the molar mass of this molecule. Sulfur is, we have 2 sulfurs, correct? Atomic mass of 32 divided by the whole molar mass. Of course, multiply by 100%. And oxygen is, you have 3 oxygen multiplied by atomic mass for oxygen divided by the whole molar mass. And this is the percentage of each of those elements present in this molecule. Now, sometimes you will see in some combustion reaction, in some type of chemical reaction, you don't have to calculate this way here, correct? Because it's everything 100% and you have 3 elements, you can say 100, correct? Percent minus this one here, 29, 1%, minus 40.5 percent, and you come up with the same value here. So because the whole sum of the percentage has to add up to 100%. Correct, guys? So let's look at this is the same thing here. And as I said, this chapter is all examples. And the only thing you have to study those examples by yourself, print them out if you want to, keep them handy if you have any problem. This is here very typical if you have hydrate, if you have a molecule that has H2O, correct? And you can determine how much is percentage of H2O inside the molecule. It's easy. It's easy. The same thing you did with the bath. You need the molar mass of the whole big molecule, correct? And the molar mass of H2O, and those are 5 of them. You divide the small amount, 5 molecules of H2O, molar mass, 5 times its molar mass, divided by the whole molar mass multiplied by 100 to give you percentage of H2O. So you have the whole molar mass of the whole copper sulfate first, correct? Here they are. That's the copper sulfate. The H2O, 5 of them here, 90. You add up the whole thing will give you the molar mass of the whole molecule. Here it is. The whole molecule molar mass. H2O is 5 of them, 90, correct? 18 multiplied by 5 is 90, and then just 90 gram per mole divided by the whole molar mass, including H2O, 5 H2O, multiplied by 100 will give you the percentage of H2O. So let's look further. I mean, it's not, the final exam will not cover all those calculations, but at least you will get the way you can get the hint how to solve those. Okay, this is the same thing here, the percentage. I want to go and look at the empirical formula here. Okay, so here it is. Need to get the empirical formula of a compound. The sample it has. Let's look at the sample here. This sample here has this amount, correct? So we can make a more empirical formula out of the sample. Sample is the whole sample. We don't know, but it does have information that carbon is this amount, oxygen is this amount, and chlorine is this amount. What is the compound percentage composition? Well, this is just the percentage, correct? So now, as we did before, you need this is how many grams you have of you have 3.10 gram, correct? And the whole mass is always the small amount, the partial amount divided by the whole compound amount. Multiply by 100 to give you the percentage. You have oxygen is 4.00 gram divided by the whole amount of the compound, give you multiply 100, give you this. And then the same thing with the chlorine. You can just subtract 100 minus the carbon 12.1 percentage minus oxygen 16.1. You get the same thing. Or you can just solve it by number of grams divided by the whole amount of the compound multiplied by 100. Now, if I have those, can I make out of this empirical formula? Yes or no? Yes. This I can assume this each one of them here is 100%, correct? So the sample is 100 gram. So this one here turns out to be 12.1 gram, okay? The empirical formula calculations start with assuming that the percentage is 100% standard gram. So this one will be 16.1 gram. This one 71.8 gram. So I transferred the 100% to 100 gram, and this is here. Next, I have to get rid of the grams to get the moles. I have to multiply by the atomic mass of each element. Carbon atomic mass is 12.1. I have to divide. I have to divide here. Let me. I have to get rid. I need the moles, correct? So I have to divide. So divide will be 12 at the bottom here. 0.0 gram per mole. So the grams with the grams cancel out. I get number of moles. Oxygen is 16. I divide this one by the atomic mass, 16.0 per mole. We get moles. And here I have to divide. The chlorine is atomic mass is 35.5 gram the top mole. So I transferred now by dividing those percentage, assuming them to be 100 gram, 100%. Then each individual element within this compound, I have to transfer its grams into moles by dividing by its atomic mass. So as soon as I get number of moles, then I divide by the least number of moles, and that's what the next step is. So that's what I get when I assume 100 grams here, guys. I assumed 100 grams of sample, and then I have the same thing here. You can see divide by the atomic, by the whatever. This is a different example, but the same thing. You get a percentage, it transfers into 100 grams, and then divided by the atomic mass of each element, you get number of moles. Now looking at this, which is the least one of all, the least one of all is this one here, 0.838, correct? Then you first divide by all of those by this small amount and see what will happen. So this, if I divide, this one will be 1, this one may be 1, and this one, I don't know what's the value, but we'll see it here together. Just hold on. So yeah, we divide it and divide that number by the previous one here. See here. So that will give you around 1, 1, 2, 3, I think, or whatever. So when you divide, it comes out to be CHCl3, chloroform. The empirical formula is chloroform. Is it the molecular formula? Yes. Sometimes the empirical formula will coincide or be equal the molecular formula. Meaning what? Meaning that the reduced ratio is equal the total ratio. You cannot reduce it further. So you have 1 carbon, okay, to 1 hydrogen and 3 chlorine, chloroform. And you know the chloroform is a compound used heavily in medicine. And so anyway, so you go further here. Now, this is the last topic of the empirical formula. This is what This is the last topic of the empirical formula. Sometimes what's happened is, and that sometimes I think is not in the ACS exam, but I think I put this one here as an example in one of the quizzes or exam. So you can expect this one will come in quiz 2 or exam 2. So this is the last thing about empirical formula. And sometimes it's very hard to know what this, you have no percentage, but then you have the empirical formula there, whatever that really is, like chloroform, CHCl3, correct? So, and then you know the molar mass. So the help of the molar mass of the whole molecule to the molar mass of the whole, of the empirical formula, you get a value of N. This is just the ratio between molar mass, empirical molar mass of the whole two value ratio divided by the molar mass of the reduced ratio. So molar mass of the molecule divided, which is a true ratio, divided by the empirical formula, which is reduced ratio. So you get the N. With the help of N here, which is a formula unit per molecule, you can do the actual molecular formula, the actual one. Okay, so let's look at an example. And I don't think that will be in the final exam, but I think if you look to this example here, just hold on. Okay, so it gives you the empirical formula of hexane C3H7, C3H7. But we know that hexane, I mean, when I tell you hexane, tell me the Tortilla hexane molecular formula, the true ratio is C6H14. So if you reduce it, you divide by a common factor. Common factor is 2. You get 3. Okay. You reduce 14 by 2, you get 7. So this is the true ratio here. And this is the molecular formula. The other one is C3, the reduced ratio, H7, that's called the reduced ratio, called the empirical formula, correct? So now we want to see, we know that the molecular formula because we know the compound, correct? But we have to calculate that's really to be true. We know that we can multiply 6 by 12 gram per mole. That's the atomic mass of carbon. And this is 14, you multiply it by 1 gram per mole. That's, we know that the whole thing, correct? But we want to see if we can get this one here calculated to us. Okay, calculated to us. So it gave you that the molecular weight is 86, but we need to get the true ratio. So it's not given to us. This is not given yet, but it's give you the reduced formula, the empirical formula. So what you will do, get your molar mass of this compound, correct? Which is by 12 gram per mole plus 7 multiplied by 1 gram per mole. Okay, that will give you the reduced amount, which came out to be here 43 here. But it's given to you here. Look at this, guys. The molar mass of the whole molecule of this molecule here of the empirical formula is this. This is the empirical formula, but I have to calculate its molar mass, but it's given to you that the whole molar mass of the whole molecule is this. What is the molecular formula? Well, it turns out to be, this is the whole thing here given to you. This is the empirical formula. So you divide those, you get N2. Correct? N2. The molecular formula given to you, it's 86.2, the molecular weight. And the empirical formula is calculated from the empirical formula ratio, reduced ratio. And then what you will do here, you get 2. Now 2, it is 2 multiplied by C3, it's 7. And the actual true ratio is 6:14. And that's what we have there. We know the answer, but we have to verify it. We have to get something like this. Okay, guys? Any question you have? So if it's no question, I will go forward and clear this. We'll go to the last topic here, which is more extensive topics we have. Let me here, guys. I wanted to bring this one out. I took me time to put those all of them in one table. So this is the stoichiometry formulas, not laws, but formulas. So the one is, we have the first one here, we have mass to the volume percentage. Okay. We have mass over mass percentage. Then we have volume to volume percentage. Those all concentration of the solutions. Concentration of solutions. And how we solve this? Mass to the volume, mass of the solute, any solution made of solute. So solution here, the solution is made of solute and solvent. Solution, solute, plus solvent. So what is solute? What is solvent? Well, it turns out to be solute is the least amount of the solution that can be dissolved by a solvent which is a larger amount. In order to have the solution, which is a homogeneous mixture, both solute and solvent, they have to have the same identical polarity, whether they are both are polar or both are non-polar, correct? So you have to have them both. So like I have solute and a solvent. I put sugar as a solute in grams, and then I put solvent H2O. I put like sugar is 2 gram of sugar solid, dissolve it in 200 mL of H2O. What is mass over the volume percentage? Well, here I have the sugar mass divided by the volume of the H2O multiplied by 100 will give me mass over the volume percentage, correct? We'll look into some examples, but at least you get the idea. Those two here, you have to watch. Those volume to volume and mass to mass, you have to watch. When I say mass to mass, the second mass here, or sometimes they call it mass percentage. Sometimes they call this volume percentage. Different from mass over the volume. Mass over mass or mass percentage, volume over the volume or volume percentage. We have to be careful about this, because when I say volume of the solute to volume of the solution, I include the volume of the solute inside the solution. So, and let's look at the definition here. Mass over mass, or mass percentage. Mass of the solute, correct, divided by mass of the solution. Note that mass of the solution is mass of both solvent and the solute. And volume is the same thing. Volume of the solute divided by volume of the solution, which is volume of the solvent and the solute both together. Anyway, so, but I want you just to look at those formula. The molarity here is a ratio. And as you can see, all those formulas are ratios, correct? Like the density, like too many ratios in chemistry we have. Molarity is a ratio. What is the ratio is all about? You relate of the solute to liter of the solution. Mole of the solute to liter of the solution. So mole to volume ratio. So let me take this one out. We go further here. We have molality. Molality, what we say? So the molarity is, if you look here further up, is we have here the moles per volume, correct? The molality here, on the other hand, is mole ratio, it's ratio, divided by kilogram of the solvent. That's a unique one. Molarity is moles of the solute divided by kilogram of the solvent. Molarity with the R is moles of the solute divided by liter of the solution. So you have to look at this, bring them out, and then you can understand how to. This one I put it there. This is very obsolete. Nobody is using equivalent, not mainly equivalent. We use just number of moles. Whenever I express molarity, it's mole per liter, mole per solute to liter of solution. Use mainly equivalent, so don't worry about it. The last one here in this is dilution. Dilution here, you come from stock solution. You have a very concentrated solution, and you have to make out of this concentrated solution diluted one. For example, you have taken a cup of coffee. That's cup of coffee, I mean, too much of caffeine. It tastes very bitter. So what you will do, you will dilute it. You will take maybe half of the cup and add some boiling tap or inside, and you can drink it. And the taste of it will be no longer that, I mean, the bitterness will be gone because you have 50% dilution. You took 50% of the amount of the caffeine inside this coffee and diluted by H2O. So dilution is always from higher concentration to lower concentration. You dilute, and it's the same thing as you heard about somebody has a lot of clots in the blood. So meaning what? The concentration of the blood will be very, very concentrated. The amount of H2O inside the blood will be less. Clotting will be of the blood is easier. So what they do, they add some chemicals that initiate, they call it blood thinner. So you make out of the blood solution concentrated, which can cause clotting. You make it thinner blood. So it's diluted blood. So to prevent any clotting. So that's an example of this dilution. Always from concentrated solution to you go to diluted solution, which is thinner, less concentrated solution. And there is a formula for that. You can use C1V1, or you can use M1V1. M for molarity and C for concentration. So you go for concentration, that's the most concentrated one. and the volume of most concentrated one will equal to concentration of the diluted one multiplied by volume of diluted one. So here it is concentrated. And here is called diluted. Okay, guys. So, and by the way, you should know that if I multiply molarity by volume, I get what? Number of moles. So this is really number of moles. Number of moles of concentrated solution equal number of what? Number of moles of the diluted one. And that's what really says. And you can replace some textbook, they don't use C concentration, they use M. M1, molarity, whatever you like, it's the same thing. So you go from the concentrated to the diluted. Now, the concentrated has another name. They call it stock solution. Stock, we are always, when we dilute, we take from the stock solution. Stock. This is a pure solution, has not been diluted at all. This came from the manufacturing company as is. We call it stock solution, and we keep it in the shelf, stock there. We're stocking the solutions from manufacturing companies inside most of the time inside special cabinets or refrigeration if needed, and those called stock solution, which is really pure, not diluted, not contaminated solution. So we can take out of this stock solution the pure, non-contaminated solution, make smaller concentration than what we started with. But we don't contaminate the stock pure solution we started with. Just take small amount out and we bring this stock solution back to the shelf or back to the refrigerator. Okay, guys? So I wanted to bring this one out because you will need, really you'll need this sheet for the calculation for calculation for this chapter. There's a question said in the chat. I think there's a question in the chat. Unmute yourself so everybody can hear you. So what's the question again? M1 V1 equal M2. I had a question here. Okay, I have to go to the chat. And I said unmute yourself and ask your question. So don't be shy. I can't talk in my. Well.
Are C1 and V1 and M1 times V1 the same thing and interchangeable?
Yes, they are the same thing. But some textbook like the M is molarity to use it, and the just preference, and the C is the concentration. But the law of dilution is the same. It's no change. Yeah, they are the same. But they're exchangeable. It depends on the preference of the author, him or herself. So yeah, they are the same. Yes.
Okay, thank you.
Yeah. Yeah, you can unmute yourself anytime. And so let me go for the next one here. This one we were talking, me and the one other professor here, and we were reviewing for 1211 and 1212, and he said that's not part of the part per million. But it's not really magic about part per million. This is another unit of concentration. The only thing is we are dealing with the mass of the solute, the same thing, divided by the mass of the solution. but then you have this power 6, which is million, correct? And this is part ppm. That will not come. He said, why you teach your student this? I said, well, I'll stop then. I'm not teaching it. Part per million, ppm, which is really you are relating the mass of your solution to the mass of the mass of the solute to the mass of the solution. Not multiply by 100% this time, like mass of, see, mass over mass. This is solute. This is solution, which is including what? The solute inside, both solute and solvent. The solution, mass of the solution is both here. Both mass of the solute plus mass of the solvent. That will be mass of the solution. Now, you can have this, or you can have the volume. Volume to the volume, volume of the solute. Volume of the solution. Volume of the solution here. Okay. So that's the same formula we did. The only thing here we have, let me just add here another color, maybe this color. You have to multiply this by 10 plus 6. So to put emphasis that it's about in million. So this here by 10 power 6. Okay. If you are talking about billion, 10 power 9. That's all. See, that's part per million. You can say part per billion, then the 6 here will be transferred into, the same ratio here, mass of the solute, mass of the solution multiplied by 10 power 6, but part per million here, instead of power 6, power 9. Instead of power 6 here, 10 power 9. And this 6 here will be transferred to 10 power 9. That's part per million. So it's nothing really mysterious about this, but don't worry, that's cancelled from, it's taken out from the, we don't teach this one because we don't have the labs to do, we can make those solutions, but we don't have the actual tools and the lab for analytical chemistry to do those, preparing those solutions. Paul said no need to give this to the students, but it's not really mysterious. It's the same like mass percentage and volume percentage. Mass is mass of the solute divided by mass of the solution, multiply by 100. But this time, not multiply by 100, multiply by 10 power 6 for part per million, or multiply by 10 power 9 to part per billion. And the same thing if you have volume over the volume percentage, volume of the solute divided by volume of the solution multiplied by 10 power 6, that's part per million, or multiply by 10 power 9 part per billion. So, as I said, this one, you don't have to print this one out. No need to print this one out. Here. And let's look at some examples here. Okay, now we are dealing with what? Examples, and that's very good because we have to learn about this. So this is the first law. I put this sheet, not sheet, this chapter, I wrote it myself because mostly it's examples. That's the whole chapter is stoichiometry, means calculation, in chemistry. So therefore, the first one here is mass over the volume multiplied by mass of the solute divided by the volume of the solution multiplied by 100. So what's given to you? The solute is small amount, which is 25 grams of kitchen salt, sodium chloride, with 450 50 mLs of H2O. Now the density from your lab is around 0.9 something, around 1 gram per ml, correct? So this 4 or 5 ml of H2O at room temperature is really 4, 5 grams, because the density of it is 1. So just to show you, this has to be the solvent, and this is the solute, small amount, correct? So this is the solute, small amount, 25 grams. And here is the solvent, is 455 grams. So this is the solvent here. Okay, guys, so now let's clear this here. And we want to see what's mass over the volume. You take the mass of the solute here, you divide it by the volume of the solution, multiply it by 100. And that's all what we did here. Mass of the solute, divide here, this is divide here, by the mass of the solution, and the answer has to be multiplied by 100%. Now you have just to watch the sig fix. This is 3, correct? 3 sig fix. And this is 3, so we have no problem. This is 3 sig fix. The answer has to be what? Rounded to 3 sig fix. Okay, guys? So let's look at another example. Next one. The next one is, will be calculate the amount of grams. Now we have, remember, this is always, I mentioned this one in the class. Remember this all the time. I said mass over the volume percentage, correct? That's the law here. Percentage equal mass of the solute divided by the volume of the solution multiplied by 100. This is a formula, correct? Main formula. How many sub formulas I can make out of it? Well, it turns out to be, I can make 2 sub formulas of this. This will be given, this will be given, that will be calculated. That's a question mark. That's one, correct? The second one, I can give you this here, correct? Give you this, and you can calculate this. So 2 sub-formulas you have to watch. So from this formula, if you look, 1 will be given, 2 will be given, then you calculate the third one. So let's look at this together and see what's given, what's not given. So calculate the amount of grams. Amount of grams means what? That's the mass of the solute, correct? That's the mass of the solute. This is the mass of solute. So here it is. This is need to calculate the mass of the solute. Solute is potassium nitrate. Potassium nitrate. And the percentage is given to you, correct? And the volume of the whole solution, the volume is given to you. So just go in and look. Mass, that's your formula here. That's your formula here. This one is given to you. This one is given. Correct? Volume of the solution is given. 100% is there. So you have to calculate what? You have to calculate. You have to calculate this potassium nitrate. Okay, guys? So one side, the left side is known. The volume of the solution is known, and the mass of the solute in green circles, you have to calculate. That's easy. So we have, this is 38.85 here. We don't know what's the mass of the solute, correct? Divided by 1 liter. Liter, always watch out for the units. This one always in milliliters. So it's 1,000 milliliter multiplied by 100. So if you look at this, you can calculate your X. Right? So calculate X, cross multiply, you can calculate your X. Now, if you verify out of calculation is this, you can verify. You can verify we came up to 38.5. You can verify this, see here, divide 38.5 divided by 1,000, multiply by 100 is 38.5. It came the same thing. Okay, guys, so next, let me clear this one here. Mass to mass percentage, that's a good one. We talked about, remember, mass of mass percentage, mass of the solute divided by mass of the solution multiplied by 100. The same thing when we were talking about part per million, part per, it's the same thing here. This is part per million. If you multiply this percentage not by 100, not by 100, the ratio is not by 100, but by 10 power 6 for billion, or 10 power 9 for part billion. Okay, guys, so here's the law. Here's the formula, guys. Okay, so this one of them will be given to you here, and the two will be given, and then you calculate the third one. So what's given to us? 48 grams. What is that? That's mass over mass. And this is 250 grams of H2O. So it turns out to be, this is our solvent, is the large amount. This is our solute. So if you divide, but you have to watch, this is just the solvent here, correct? And this is the solute. So what is the mass of the solution will be the sum. You have to add this to this. That will be mass of the solution. Mass of solution is 250 plus 48. Okay, that's mass of the solution. Okay, so, and then mass of the solute is 48. So it's really 48 here. Look at this. Divided by the mass of the solution, 48 plus 250, multiply by 100, I'll give you what? I'll give you the final answer, 60 gram over gram mass solute to mass of the solution percentage. So, and another example, we'll go volume to volume. We'll go volume to volume. Okay, so here's the same thing, guys. Just something is given to you and something you have to the sub-formulas. This is sub-formulas. Why I'm saying sub-formula? Because it's give us the mass percentage, mass to mass percentage, and it give us the amount of the solute here. And it's asking about what is the mass of the solvent, correct? And this is the solute here. It's asking the solvent, correct? It's asking what? The mass of the solvent. So how we do that? Well, mass percentage is, or the mass number, mass percentage or mass to mass percentage is mass of the solute divided by the sum of the mass of the solute plus the sum of the solvent. Here is the formula again. We have to, this is, what is the formula here? It is, let me take this one out here. Guys, that's the formula here. Mass percentage, mass to mass, you can see mass of the solute divided by mass of the solution. Mass of the solution here is defined as mass of the solute plus mass of the solvent. So let's do it together. So we have the solute 10.50, that's a percentage here. Divided by 100 because 100 percentage. Mass of the 2.00 gram solute divided by X. The mass of the solution you don't know, but you know this, you know the what, you know the solvent. So it will be, here it is. You calculate your X to know what is the mass of the solution. X is mass of the solution, not mass of the solvent yet, because X is mass of the solution, which is include the mass of the H2O solute, solvent, sorry. Okay, so you get out the X is 19. Okay, and you have 2 of this is the solute. So 19 minus 2 will give you 17. So the answer is 17. Okay, guys. One more minute and then we'll conclude this chapter here. One more minute. Just bear with me a little bit. Volume to volume, and then I'll stop here. Volume to volume is the same thing. Volume to volume percentage or volume percentage is volume of the solute in the top divided by volume of the solution. What is volume of the solution? Is made of volume of solute plus volume of the solvent. So you can have two subformulas the same way. So here it is. The question here is given to you volume to volume. What's the percentage by volume is the formula here. You can make out of these two subformulas. It's neat. What is the percentage? Give me the volume of the solute and the volume of the solvent. So the solute volume in the top, correct? This is the top, is the solute volume divided by, you have to add this to this, will be the volume of the solution. And that's what we have here. So this one here, volume of the solute divided by the sum of both solute and solvent multiplied by 100. And that came out to be, and watch for 6 weeks, it came out to be 14%. So it's time is up, 9:45. Thank you very much for listening. And I promise to put this one here as soon as I get recording. It takes time. Maybe night I will get the recording back and I'll put it my YouTube, and then we'll try from there, post it in the iCollege. Okay, guys, let me just stop sharing here. And thank you very much. Now I can open just before closing the class. Any question you have?
Do we also have one for, do we also have a WebEx for lab today?
Yes, in 15, 20 minutes.
Okay,
And if
thank
you
you.
like, I can make it 30 minutes. So you'll have time to go and eat something and come back. 30
Okay,
minutes.
great.
So we'll start 10:30 for the lab.
Start at 10:30? All right, thank you.
Yes, 10:30. Yeah.
All
Thank you
right.
very much. I'll stop recording now. Thank you.